This video gets you started using SystemVerilog assertions. Imagine a very simple bus protocol that requires 7 signals. The environment asserts the reset signal to reset the arbiter state. The devices assert their request signal to request access to the bus. The arbiter asserts a grant signal to grant a device access to the bus, while rotating priority in a round-robin manner. The granted device places data on the bus and asserts the data-ready signal. The granted device asserts the done signal in the last cycle of its bus access. And the arbiter asserts the busy signal with the grant signal, and otherwise removes it in the cycle after done. Here is an example of two-word data transfers. On the first cycle, the arbiter grants the device 0 request and raises the busy signal. On the second cycle, device 0 lowers its request, drives first data onto the bus, and raises its data-ready signal. Device 1 coincidentally makes a request that the arbiter cannot yet grant. On the third cycle, device 0 drives second data onto the bus, raises its done signal, and makes another request that the arbiter cannot yet grant. On the fourth cycle, device 0 lowers its done signal and its data-ready signal and removes its data from the bus. The arbiter grants the device 1 request and maintains the busy signal. On the fifth cycle, device 1 lowers its request, drives first data onto the bus, and raises its data-ready signal. On the sixth cycle, device 1 drives second data onto the bus and raises its done signal. On the seventh cycle, device 1 lowers its done signal and its data-ready signal and removes its data from the bus. The arbiter grants the device 0 request and maintains the busy signal. On the eighth cycle, device 0 starts the second bus access. An assertion is a statement that a design property is true, that is, that it exhibits some particular behavior, and is also a directive to verification tools to verify that the property is true. But I get ahead of myself. Let's instead start at the bottom with, what is a Boolean? A Boolean is an expression of design states and or numerical literals that has a Boolean true or false value. What is a sequence? A sequence is an expression of successive Boolean expressions evaluated over one or more cycles, usually clock edges. You compose sequences from Booleans and other already composed sequences. You generally cover a sequence. That answers the question, did the sequence occur? What is a property? A property is typically an expression of successive sequences, chained by implication. You can typically express a property as an if, then, else expression. You compose properties from Booleans and already composed sequences and other already composed properties. You generally assert a property. That answers the question, does the property hold? That is, does the design exhibit that behavior? Let's assert that a request implies an eventual grant. The assert property statement syntax is, in order, the assert keyword, the property keyword, the parenthesized property specification, and an action block. An action block is similar to an if statement, but with the if keyword assumed. An action block has a pass branch and a fail branch. You can omit either branch or the entire block. If you omit the action block, you must replace it with a null statement, that is, a semicolon. Following this syntax, we have labeled the assertion statement and provided an action block having only the fail branch. The property specification syntax is, in order, an optional clocking event, an optional disabling clause, and a property expression. The clocking event can be almost any event. Most people use a clock edge. All asserted properties are somehow clocked. The clock can be part of the property expression, part of the property specification, or default clocking. The disabling condition, while true, disables any ongoing or new attempts to evaluate the property. Following this syntax, we provide a clocking event and a disable clause. The property expression syntax accommodates many forms of expression. One of those forms is an instance, potentially parameterized, of a declared and defined property. Following this syntax, we instantiate the request grant property and pass into it the request 0 and grant 0 signals. Now, let's go ahead to declare and define the request grant property. The property declaration syntax is, in order, the property keyword, a property type identifier, an optional property port list, optional declarations of local variables, a property specification, the end property keyword, and an optional repetition of the property type identifier. Some of this syntax we will not utilize. Following this syntax, we declare the request grant property, providing input ports for the request and grant signals. The property specification syntax is, in order, an optional clocking event, an optional disabling clause, and a property expression. Some of this syntax we will not utilize. The property expression syntax accommodates many forms of expression. One of those forms is sequence implication. This form is next cycle implication. The cycle in which the left operand sequence behavior completes requires the right operand property behavior to start in the next cycle and complete in whatever is the required cycle of completion. Failure of the left operand to complete is a vacuous pass. The attempt vacated. It went away. Failure of the right operand to complete is failure of the attempt. Following this syntax, we insert a next cycle implication operator, an antecedent left operand sequence placeholder, and a consequent right operand property placeholder. The sequence expression syntax accommodates many forms of expression. One of those forms is a Boolean expression or distribution, followed by a Boolean abbreviation. A Boolean abbreviation is a syntax for concisely applying repetition. We do not utilize it here, but will later, and so later we'll explain it. Following this syntax, we replace the antecedent left operand sequence placeholder with a Boolean system function. This function is true in the cycle in which its argument is 1 and was not 1 in the previous cycle. That is, it rose. We use this function instead of the signal itself because a device typically maintains its request until granted. We want only the first of those cycles to start an attempt on the consequent right operand property. The property expression syntax accommodates many forms of expression, among them a sequence expression. The sequence expression syntax accommodates many forms of expression, among them a cycle-delayed sequence expression. The delay expression can be a single constant integer or a range between two constant integers. The integers can be anything between 0 and infinity. The range left bound must be no higher than the right bound. The delay expression syntax provides two range abbreviation characters. The asterisk, which we will use here, is the range 0 to infinity. The plus is the range between 1 and infinity. Following this syntax, we replace the consequent right operand property placeholder with a cycle-delayed sequence. The delay is any integral value between 0 and infinity. The sequence is the grant signal passed into the property upon instantiation. You can accomplish exactly the same result with same cycle implication and a delay of at least 1. Does this solution have something wrong with it? It actually does, and unless you already knew it, well, you wouldn't know it. The sequence implication property expressions are by default weak. That means that if an attempt on the property is ongoing and your simulation terminates for any reason, the simulator does not report a failure of that attempt. How is that a problem? We have stated that upon making a request, the grant can arrive in any cycle after that, including the cycle before infinity. Formal analysis tools can figure this out. Simulators must actually crunch those cycles. So for simulators, time is necessarily finite. Simulators cannot fail this property because, who knows, maybe the cycle after simulation terminated is the cycle in which the grant would have come. So we have a conflict here. We want to verify the property, but we also want the simulator to not, upon termination, report a failure of an ongoing attempt. To verify the property, we could rewrite it as a strong property. If an attempt of a strong property is ongoing and your simulation terminates for any reason, the simulator does report a failure of that attempt. To rewrite this as a strong property, you can make the consequent sequence strong, or you can just use the strong eventually property operator. This actually verifies the property. But now, if an attempt of the property is ongoing and your simulation terminates for any reason, the simulator reports a failure of that attempt. Is this what you really want? To verify the property, we could keep it as a weak property, but put some upper limit on the eventually part. That limit can be the longest delay you can possibly stand before the grant absolutely must occur. To put an upper limit on the eventually part, you can define your own range, either as a cycle-delayed sequence or as a limit on the weak eventually property operator. Let's next assert the property that the grant signal is true for only a single contiguous cycle. As we continue to use the same clocking, On the same disabling condition, for our convenience, let's declare these to be the default clocking and the default disabling condition. As before, we state the assertion, this time without the clocking event or disabling condition, and again postpone the property expression declaration. You have previously seen all of this. We declare the property to take any signal. The property expression is a next cycle implication. The left operand is a sequence. Recall that a signal is a Boolean, which is one kind of sequence. The right operand is a property. The inversion of a Boolean is obviously also a Boolean expression. A Boolean is a kind of sequence, and a sequence is one kind of property. The property expression thus matches the syntax requirements. The property is that if any cycle finds the signal true, then the next cycle finds it false. Let's next assert the property that a grant implies also busy, and the busy stays true until and with the done signal. As before, we state the assertion and postpone the property expression declaration. One of the many things that a sequence expression can be is two sequence expressions connected by a cycle delay range. You previously saw that a cycle delay range can be a constant or a range between two constants, and that you can use shortcut characters to represent some common ranges. The implication antecedent sequence is the first signal. The first signal implies that something further occurs. That something further starts on the same cycle, so we need same cycle implication. The implication consequent property, here simply a sequence expression, consists of two sequences connected by a single cycle delay, thus is sequence concatenation. The second sequence of the concatenation is the Boolean expression that both signal 2 and signal 3 are true. What is the first sequence of the concatenation? Another of the many things that a sequence expression can be is a repetition of a Boolean expression. The repetition can be consecutive, non-consecutive, or go to. The go to repetition is a variant of non-consecutive repetition. We will use consecutive repetition to represent something that occurs multiple times consecutively. So the first sequence of the consequent sequence concatenation is any number of cycles with the second signal true. The first signal implies that the second signal is true and stays true until and with the third signal. For this property expression, the operator precedence just happens to work well. The repetition operator has higher precedence than the cycle delay operator, which has higher precedence than the implication operator. Keep in mind that you can force precedence as needed by parenthesizing expressions. Let us next assert the property that the arbiter priority rotates in a round-robin manner. How would we express that? We can express that as, if any given device makes a request, then all other devices get at most one grant each before the given device gets its own grant. To write this property generically is interestingly difficult and not practical here, where no grant vector exists. However, it can be done. To write this property non-generically, you have previously seen everything that you need to know. We state the assertion and postpone the property expression declaration. Grant zero fairness is simply that any cycle in which device 0 is making a request and device 1 is getting a grant implies that on the next cycle, the device 1 grant stays low until device 0 gets a grant. You can likewise declare, define, and assert a grant 1 fairness. What is the difference between an assert and a cover? You assert a property. Upon assertion failure, the simulator reports an error message and sets the error status flag. You typically cover a sequence. SystemVerilog permits you to also cover a property. The simulator counts completions of the sequence or property. For the cover directive, the simulator does not issue a message upon failure to complete. For the assert directive, the language reference manual requires the simulator to count the attempts, total passes, vacuous passes, and disabled attempts. The Xcelium simulator, by default, counts the number of times an assertion finished, failed, or was disabled. Use the simulator command assertion with its option to turn on strict interpretation to interpret the SystemVerilog language reference manual more strictly. For the cover directive, the language reference manual requires covering a sequence to report the number of times attempted and the number of times matched, and covering a property to report the number of times attempted, the number of times completed, and the number of attempts vacated. The Xcelium simulator, by default, counts covers only once. Covered is covered. The document, Assertion Checking in Simulation, describes how to modify this behavior. To remember this is important. You frequently describe design behavior by using regular expressions. Design behavior can frequently match more than one expansion of the regular expression. A sequence is a property, so you can cover it as a property. But each attempt of a property can only once fail, finish, or be disabled. Covering the sequence as a property can count at most one completion of each attempt. Covering the sequence as a sequence can count all the completions of an attempt. Let's cover that the devices did a data transfer taking between 1 and 3 cycles. The cover sequence statement syntax is in order: the cover keyword, the sequence keyword, an optional clocking event, an optional disabling clause, a sequence expression, and a statement. We have already examined the clocking event and disabling clause. The simulator executes the statement upon each completion of the covered sequence. The statement is required, but can be a null statement. Following this syntax, we label the cover statement, provide a clocking event and disabling clause, insert a sequence expression placeholder, and for the statement, display an appropriate message. The sequence expression syntax accommodates many forms of expression. One of those forms is an instance, potentially parameterized, of a declared and defined sequence. Following this syntax, we instantiate the data123 sequence and pass into it the grant 0 signal. Now, let's go ahead to declare and define the sequence. The sequence declaration syntax is in order: the sequence keyword, a sequence type identifier, an optional sequence port list, optional declarations of local variables, a sequence expression, the end sequence keyword, and an optional repetition of the sequence type identifier. Some of this syntax we will not utilize. Following this syntax, we declare the data123 sequence, providing an input port for the grant signal. The sequence expression syntax accommodates many forms of expression. One of those forms is a cycle delay separated sequence of sequence expressions. You have previously seen the syntax for cycle delays. Another sequence expression form is a Boolean expression or distribution, followed by a Boolean abbreviation. A Boolean abbreviation is a syntax for concisely applying repetition. It is a Boolean abbreviation because it applies to Booleans. The repetition can be in consecutive cycles, cycles that may or may not be consecutive, thus termed non-consecutive, although consecutive cycles also fit the non-consecutive definition, and a variant of non-consecutive repetition termed go-to repetition. The go-to repetition limits the number of potential matches, which in pure non-consecutive repetition can be infinitely many. Following this syntax, we define a sequence expression that is a cycle with grant true, followed by 1 to 3 cycles, not necessarily consecutive, in which the data ready signal is true, and with the done signal true in any of those cycles in which the data ready signal is true. Here, the go-to repetition range creates 3 potential matches for design behavior. The first match is up to the cycle in which the data ready is true for the first time. The second match is up to the cycle in which the data ready is true for the second time. The third match is up to the cycle in which the data ready is true for the third time. The 0 cycle delay means that done occurs coincidentally with data ready, with 0 delay between them. Here is the simulation analysis environment, commonly called SymVision, waveform window, displaying in transaction form our assertions and cover. No assertions failed during this test. The Xcelium simulator, by default, does not count covers. You enable counting covers by either enabling functional coverage during elaboration or by using the interactive simulator command assertion with its options to turn on covers. The Xcelium simulator, by default, probes assertions, and if enabled, covers as states, that is, active, inactive, finished, failed, or off. You can alternatively probe them as failure events or transactions by selecting the assertions and covers, selecting their menu item Create Probe, and in the Create Probe dialog, selecting either failure events or transactions. Here, the Integrated Metrics Center summarizes the assertion coverage metrics, all sequences and properties completed at least once.